On this question, we want to solve the exponential equation using the method of relating the bases by first rewriting the equation in the form b to the u equals b to the v. The equation that we'd like to solve is 3 to the x minus 6 equals 1 over 27. So before we start solving this equation, let's discuss this method of relating the bases. So the method of relating the bases starts off with you writing your equation in this form, b to the u equals b to the v. This is very important for the method because the method requires that we have the base on each side of the equation being the same. And when the base on each side is the same, we can use a property of exponential functions, the one-to-one property. This is a property that we've discussed in previous chapters. The one-to-one property, it doesn't just apply to exponential functions, it applies to many types of functions. But what it tells us is that if the y's are equal to each other, if we have two y values that are equal to each other, then those x values must be equal to each other. And that's what we're going to use once we've written the expression in this form, or the equation in this form. We consider this left-hand side to be a y value and the right-hand side to be a y value. And we've got the equal sign stating that they're equal to each other. And the exponents, these are the x values. And because we have an exponential expression on each side, we can say that these exponents are equal to each other. This works because exponential functions have this one-to-one property, and you can say that when the y values are equal, the x values must be equal. So that's what we're going to use in this equation. So what's nice is that you start off with an equation that's an exponential equation, and once you apply the property, you've simplified it to another type of equation. Usually it's going to be a linear or quadratic equation from this point here on. So our equation is 3 to the x minus 6 equals 1 over 27. So our first challenge is writing the equation in this format. We want to have the bases match each other. I have a base on the left of 3, and I'm going to try to write the right-hand side with a base of 3. 27 is the same thing as 3 cubed. So I can write this as 1 over 3 cubed. Now I don't want that in the denominator, so I'm going to move that factor to the numerator, and we can put a negative on the exponent using our exponent properties in order to move that factor to the numerator. So now we've written it so that we have the same base on both sides, and we can use this method of relating the bases, this one-to-one property, and say that these exponents have to be equal to each other. So we have the equation x minus 6 equals negative 3. X minus 6 equals negative 3 is a linear equation. I'll add 6 to both sides and get x equals 3. So we have the solution to our equation being 3. On this question, we want to solve the exponential equation using the method of relating the bases by first writing the equation in the form b to the u equals b to the v. The example we're working with is square root of 3 equals 9 to the x. So we're going to start by rewriting the equation in this form. And the reason why we want to do that is because then we can apply the one-to-one property that exponential functions have. So once we have the bases the same, we're going to be able to say that the exponents are equal to each other. So with this example, I have a base of 3 on the right. I can rewrite that square root as 3 to the 1/2 power. And 9 is a power of 3. I can write 9 as 3 squared. And it's still raised to the x power. On the right-hand side, I'm going to simplify using the power rule for exponents. The power rule for exponents is this here. If we have a to the n, then raised to the m, we have a power raised to a power, then we multiply those powers together. So we get n times m. So for our example, we have 3 squared to the x power. We're going to multiply those powers together, get 3 to the 2x. On the left-hand side, we have 3 to the 1/2. So now we've written it so that the bases are the same. And by that one-to-one property, the exponents must be equal to each other. That gives me the equation 1/2 equals 2x. And I'm going to finish solving this equation by dividing by 2 on both sides. That's x equals 1/2 divided by 2. That's 1/2 times 1/2. 1/2 times the reciprocal, and that's 1/4. So we have the solution being x equals 1/4. On this question, we want to use the periodic compound interest formula to answer the following question. How much money will you have in 6 years if you invest $18,000 at 5.5% annual interest rate compounded quarterly? And how much will you have if it's compounded monthly? So we want to use this periodic compound interest formula, which I have written down here. So this is the formula, A equals P times 1 plus R over N to the NT. And I've also listed what each one of these variables stand for. So the P is the principal or your initial investment. The R is the annual interest rate. N is the number of compoundings in 1 year. Now that word can be a little bit confusing, but what it means is how often your interest is added into the account. T is time in years, and A is the accrued amount. So I'm going to read my problem again, and as I read through the problem, I'm going to try to identify these numbers matching with these variables that we have. So in reading the question, we have how much money will you have in 6 years? So that 6 is referring to T, the time. If you invest $18,000, $18,000 is our initial investment, which is our principal. We're going to invest that $18,000 at a 5.5% annual rate of interest. So this is our rate, our interest rate, 5.5%. And when we use this value in our formula, we don't leave it in percentage form. We put it in decimal form. So we're going to take that decimal place and move it 2 places to the left, giving us 0.055 as the value we'll use in the formula. This annual interest rate is compounded quarterly. Quarterly is how often the interest is added into the account. So this is going to give us our value of n. If the interest is compounded quarterly, that means that the interest is added in 4 times a year. So n is 4. So we've got all of our values in the formula. We're going to substitute into the formula to get the accrued amount. That's how much money we will have after 6 years. So A equals 18,000 times 1 plus 0.055 over 4 raised to the 4 times 6. We're going to type our values into the calculator. This particular calculator will allow you to type the entire expression. We have 18,000. Let's try that again. 18,000 times 1 plus 0.055 over 4 raised to the 4 times 6 power. So we are going to have $24,981.20 at the end of the 6-year time period. Let's write that down. $24,981.20. Now, if you don't have a calculator like this, and you need to type in each individual operation, this is how you would type it. You want to make sure you follow order of operations. So you're going to start inside the parentheses, and you're going to do the division first, 0.055 divided by 4. We're still inside the parentheses, and we need to do the addition. We're adding 1. And exponents come before multiplication, so I'm going to do the exponent of 24 and then multiply by the principal of 18,000. And you can see we have the same value, $24,981.20. Now there is a second part to this problem. And the only difference on this part is that we are asked to compound monthly instead of quarterly. So this is only going to change the value of n. So we're going to change the value of n to be 12. We compound monthly, that is 12 times a year. Interest is added in. Everything else in our formula will be the same. 18,000 times 1 plus 0.055 over 12 raised to the 12 times 6. Let's bring my calculator back and we'll type that in. We have 18,000 times 1 plus 0.055 over 12. Excuse me, let me correct that. Divided by 12. And then raised to the 12 times 6. So this time we got $25,018.56. Notice I'm rounding to the nearest cents because we're talking about money. So we have $25,018.56. And you'll notice here that since we compounded the interest, since we added the interest more often, we have a little bit more money in the account because of that. When you do that, you start earning interest on your interest a little bit faster. So if you're able to compound or add interest in more often, your account will grow a little bit faster. For this question, we have a word problem related to population growth. In 2007, the population of a certain city was 15,405. If the relative growth rate has been 6.1% since 1980, what was the population of the city in 1980? Use the exponential growth model P of t equals P naught e to the kt. So this is the exponential growth model, which we have written down over here. P of t equals P naught e to the kt. Let's take a moment to explore the different values here, the different variables. P naught is the initial amount, the initial population. This P naught, it has a 0 here. That's what I'm calling the naught. And it's meant to mean, it's like a shorthand for saying P at time 0, which we generally write P of 0. So it's sort of like a shorthand for that. And that's why we call it the initial amount or the initial population, because time 0 is the beginning, the initial. K is the growth rate. So we are given that growth rate. T is the time, and this can be in whatever units. This problem, the units happen to be in years. And then P, this variable on the left, P, is the population after that amount of time. So the way that this model works, the growth model, you put in a time, and it's going to tell you the population at that time. So let's read through the problem again and see if we can identify any of the variables in this question. It says, in 2007, the population of a certain city is 15,405. So in 2007, we have a population of 15,405. So this is a pair of information that goes together. This part is going to help us with the time t, and this is our population at that particular time. Let's keep reading. The relative growth rate has been 6% since 1980. So K will be our growth rate, 6.1%, and we're going to use that in the decimal form. So I'm going to move my decimal place 2 places to the left to get 0.061. So this is our growth rate since 1980. What was the population of the city in 1980? So we're going to use 1980 as our initial time, as our time 0. So our goal in this question is to figure out the initial population P naught, or P sub 0. That's our unknown. So going back to this information that we had at the beginning, in 2007 we have a population of 15,405. What I need to know is what value we're going to use for t. And that t is going to be 2007 minus 1980, the number of years since 1980. So let's work that out. How many years since 1980? 2007 minus 1980 is 27 years. So in 2007, we have a population of 15,405. P of 27, the population 27 years after 1980 is 15,405. I think we have enough information for us to substitute some values into our model and solve for our missing population. So once again, our model is P of t equals P naught e to the kt, and P naught is our missing value. So we're going to leave that variable alone, and we're going to substitute into the other values. By the way, I haven't mentioned this yet. This e, the e in the formula, is not a variable. E is the number 2.718, and those decimal values continue on forever without repeating a pattern, very similar to how we use pi in formulas. K, we said, was 0.061. Our time is 27 years, and our population at 27 years is 15,405. I can solve for this initial population, this population in 1980, by dividing both sides by e to the 0.061 times 27. So we're going to get the calculator out and type this value in. We have 15,405 divided by any parentheses around my denominator. The E button here is on ln, above ln in blue. 0.061 times 27. And I need to close parentheses for the denominator. So we got 2,967.41, and let's round to the nearest whole number. So we're going to say 2,967. So the initial population is 2,967. Let's double check. Yes. So the population in 1980 is 2,967. Solve the exponential equation using the method of relating the bases by first rewriting the equation in the form b to the u equals b to the v. The equation we're working with is 5 to the x cubed power equals 25 to the x over 5 to the negative x squared. We're going to use the method of relating the bases. And we're going to start off by writing in the form b to the u equals b to the v. And the relating the bases method says that once the bases are the same, the exponents must be equal to each other. So we're going to be able to simplify the equation to be u equals v. Now we have some work to do to rewrite the equation in this format starting off. As I look at this example, let me write it a little bit larger. We have 5 to the x cubed equals 25 to the x over 5 to the negative x squared. So as I look at the bases that I have here, I have 5, 5, and 25. I want to try to write all of these expressions with the same base. When you write them with the same base, you have all kinds of properties that you're allowed to use. So let's rewrite the 25 with a base of 5 so that we have all the same base. And 25 is equal to 5 squared. So that gives me 5 squared to the x over 5 to the negative x squared. So now I'm going to simplify this expression in the numerator with the power rule for exponents. The power rule for exponents gives us this property, b to the m to the n. So if we have an exponential expression that then is raised to a power, we can multiply those powers together to get b to the m times n. So that's going to allow me to rewrite this as 5x cubed equals 5 to the 2x over 5 to the negative x squared. So I multiplied that 2 and x together. And then I'm going to simplify this right-hand side using another property of exponents called the quotient rule. This is the quotient rule for exponents. And with the quotient rule, if we have a fraction, that's why we call it the quotient rule, and we have the same base in the numerator and the denominator. Let's say we have b to the m over b to the n. If we have the same base with expressions being divided, we're going to subtract the exponents. So that's going to give b to the m minus n. Sorry about that, my whiteboard's acting a little funky. So on the right-hand side here, we will notice that we do have the same base, so we can apply that property of the quotient rule to get 5 to the 2x minus negative x squared. So let's simplify that subtraction in the exponent. We would have 5 to the 2x plus x squared on the right-hand side. And now we have written it so that the bases are the same on both sides. So now that we've written it with the base being the same on both sides, we're going to apply that relating the bases property or the one-to-one property and say that the exponent on the left, x cubed, is equal to the exponent on the right, 2x plus x squared. So this gives me a polynomial equation, and I'm going to solve this with factoring. I'll move all the terms to the same side. That's going to give the equation x cubed minus x squared minus 2x equals 0. I'll start factoring the greatest common factor of x. I factor out that x, I'm left with x squared minus x minus 2 equals 0. And x squared minus x minus 2 is a quadratic, and I'll try to factor that. x times x is x squared. 2 times 1 is 2. And I need the negative on the 2 and a positive on the 1. And I'll set each of these factors equal to 0. X equals 0, x minus 2 equals 0, x plus 1 equals 0. And that gives solutions of x equals 0, x equals 2, and x equals negative 1. So we have 3 solutions to this exponential equation. I'm going to zoom out so we can see the whole thing at once. So we had to apply some properties of exponents to get it in the right format. And once we did that, we were able to relate the bases and solve the remaining equation. For this question, we want to solve the exponential equation using the method of relating the bases by first rewriting the equation in the form e to the u equals e to the v. We have the equation e to the x squared equals e to the negative x times e to the 30th. So this method that we're going to be using, relating the bases, has us rewriting it so that we have e to the u equals e to the v. And once we have those bases being the same on either side of the equation, then we can say that the exponents are equal to each other. And we would have u equals v. So we're going to start off this question trying to write the equation in this format so that we have the bases being the same on both sides. So on the left, we already have e to the x squared, so we don't need to make any changes to that. On the right-hand side, we're going to use a property of exponents called the product rule to combine those two expressions together. We can use that product rule because they have the same base. So let me show you, this is the product rule for exponents. And it says when you have b to the m times b to the n, when you're multiplying, it's called the product rule because we're multiplying. We're multiplying with the same base. And when you do that, you can add the exponents. So we have the same base and we add the exponents. So for our example, we have e to the negative x times e to the 30th. They have the same base. So we're going to be able to add those exponents and get negative x plus 30. So now we have the same base on each side of the equation. And we're going to apply that relating the bases method. And once those bases are the same, the exponents have to be equal to each other. We have x squared equals negative x plus 30. So this has given us a quadratic equation, and I'll solve this by moving all the terms to the same side and factoring. So we have x squared plus x minus 30 equals 0. We'll factor. That gives x and x. 30 we can factor into 5 times 6. I chose 5 times 6 because I could create the 1 in the middle that I need. So I'll put a plus on the 6 and a minus on the 5. We'll set each one of these factors equal to 0 and give x equals 5 and x equals negative 6 as the solutions to this exponential equation. On this question, we want to sketch the graph of the exponential function f of x equals 1/7 to the x. We're going to sketch a graph by plotting points. So we're going to choose some x values, and the x values that we choose here are just going to be a sort of a standard set of x values that I always default to, and that's -2, -1, 0, 1, and 2. And we're going to substitute those into our function f of x to get the y values. I'm going to start with the values that are a little bit easier to work out. So we're going to do 1/7 to the first power, and any number raised to the first power is itself. So this is 1/7. And let's do 1/7 to the second power. That'll be 1/49. And then we're going to do 1/7 to the 0 power. 1/7 to the 0 power is 1. And any number to the 0 power is 1 except for 0. That value will be indeterminate or undefined. And 1/7 to the -1 power. When we have a negative in the exponent, that means that we can do the reciprocal of the base to apply that negative. So to get rid of that negative, we're going to do the reciprocal of 1/7, which is 7. We have 7 to the first power now. So 7 to the first power is 7. And we'll do the same thing on the next one, 1/7 to the -2. The negative allows me to do the reciprocal of the base, so that's 7 squared is 49. So this gives me some points to plot. We will plot 0, 1, and 1 and a 7th, and a 49th, 2 and a 49th. -1 and 7 would be about here, and -2 and 49 goes off of our grid. So we can tell that this end is getting large very quickly. It goes off to infinity. On this other side, where x is getting larger and larger, you can see our y values are getting smaller and smaller, getting closer to 0. And so this is going to get closer and closer to our x-axis, closer to a y value of 0. And this exponential function, like other exponential functions, has a horizontal asymptote. This horizontal asymptote is right on top of the x-axis, the line y equals 0. So we have a sketch of our function f of x equals 1/7 to the x power. On this question, we want to sketch the graph of the exponential function, label the y-intercept and at least 2 other points on the graph using both positive and negative values of x. So we're going to make a chart and sketch this graph by plotting points. I'm going to choose some values of x, and I'm going to go with my standard set of x's. That's -2, -1, 0, 1, and 2. And this satisfies what's being described here. You want to find a y-intercept. That's when x is equal to 0. So we are substituting an x value of 0. And then we want to find at least 2 other points using both positive and negative x values. So you can see we have more than that, with 5 points with positive and negative x values. We're going to substitute this into our function, and because the base that we're using in this example, we have f of x equaling -5 e to the x. E is approximately 2.718, and so we don't get very nice clean y values in this example. So we're going to get our calculator out and find approximate values for the y so that we're going to be able to draw the graph. So let's substitute these values in, and then we will approximate them with the calculator. So this is negative 5 e to the negative 2, negative 5 e to the negative 1, negative 5 e to the 0. This one works out nicely because any number to the 0 power is 1, and except for 0. So we get negative 5. So that's really the only nice y value. Negative 5e to the 1, negative 5e squared. So we're going to use the calculator. And let me pull it up. And you can type the first one, that's negative 5e to the negative 2. And that is approximately negative 0.677. Let's find the next one. That's negative 5e to the negative 1. And that is approximately negative 0.839. Negative 1.839. And let's take a look. Maybe my calculator won't go away every time if I do this. We've already worked out negative 5e to the 0, but let's just confirm it here. Negative 5e to the 0 power gives us negative 5. Negative 5e to the first power is approximately 13.591. We have negative 5e squared is approximately negative 36.945. So now we have the approximate values of our y, and we can plot the ordered pairs. We've got negative 2 and negative 0.677. That would be about right here. We have negative 1 and negative 1.839. That's almost negative 2. We have our y-intercept at negative 5. And then 1, and I may have left off a negative here. So let me look at that calculator one more time. Yes, I left off that negative. So 1 and negative 13 puts us off our grid. And we have a sketch of our graph of negative 5e to the negative, e to the x. We do have a horizontal asymptote that is right on top of our y-axis, our x-axis, the line y equals 0. Thank you for checking out my videos. Have a great day.